Okay. So, in the last class we had been considering these random sequences, or maybe you can call a random vector. If the sequence has just a finite number of terms, you can put them in a vector form. So, today we continue from that. We consider this topic of conditional probability density of a random vector. Let us suppose we have got this sequence then this thing that is giving the values of x1, x2 up to xk, condition to that, what is the probability density of xn, xn minus 1 up to xk plus 1. Okay, this as before is nothing but the ratio of two joint densities. One is there is a total joint density of all the n variables divided by the joint density of the variables which are conditioned here, that is xk down to x1. Okay. And you can easily define using this what is then conditional distribution. Okay. After all, you have to just integrate, that is the conditional distribution is nothing but just an integral. That is, you have to just integrate this conditional density function with respect to this variables xn, xn minus 1 down to xk plus 1 over their entire range. No, sorry, from minus infinity up to the value xn to xk plus 1. Okay. So, we just change these variables, bring maybe say alpha n, just give them new names to alpha k plus 1, condition to alpha k dot 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 alpha 1, and integral. So, I am running short of space here. So, let me erase some part. D alpha n down to d alpha k plus 1, and the limits are minus infinity to x n, that is for alpha n, dot 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 minus infinity to x k plus 1. Okay. That is, we are doing nothing new, we are only extending our concept of conditional probability density and distribution function from one variable and then two variables to, in general, a set of n variables. Okay, nothing else. The basic philosophy remains same. Just for example, you can say that p x1 by x2 x3. Okay, this is nothing but p x1 x2 x3 divided by p x2 x3. Okay. And this probability density is nothing but like its integral with respect to x1 was giving you the conditional distribution. That means this density is nothing but the derivative of the distribution with respect to x 1. That is, you can also write this as df x 1 by x 2 x 3 dx 1. Okay. We can form a chain rule using these. That is, you can now write like this. First isolate x n. So, P of x n subject to or condition to the other ones multiplied by the corresponding joint density of these remaining ones. Then this again you express like this, that is this remains as before. The second term you express like this, conditional density of x n minus 1 subject to the rest, there is x n minus 2 downward to x 1 times the joint density of x n minus 2 up to or down to x 1. And likewise, if you continue, finally you get this dot 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 P of x 2 by x 1 into P x 1. This is a chain rule. It is very useful at times. We will take an example to show how this rule sometimes becomes very useful. Okay. Suppose is a random vector. Okay. So, it has got some joint density, then conditional densities, conditional distributions and all those things, okay, as defined just a while back. Okay. Suppose we form this quantity first, y 1, which is nothing but the distribution of x 1. Now, my claim is y 1 is a random variable. After all, f of x 1 is nothing but a function of x 1. So, whenever x 1 takes a value, you get a value of this function f x 1 and that is assigned to y 1. Okay. So, if x, I mean anytime x takes a value x 1, f of x 1 means what is the total probability of the random variable x 1 taking values from minus infinity up to that. So, you get some value. Next time x 1 value changes, so f of x 1 also changes, so on and so forth. Obviously, y 1 is a random variable, but it is a function of only one random variable x 1. One random variable, that is x 1. Then define y 2 as conditional distribution of x 2 given x 1. Again, for some for any two values of, for any specific values of x 1 and x 2, you get some value for this distribution function and give it to y 2. But at x 1 and x 2 change with experiment to experiment, the value y 2 also changes. That means y 2 is a random variable, but this time is a random variable of that is a function of two random variables x1, x2. Likewise, we define dot 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 y8 as okay. So, you get n random variables. First one is a function of only one random variable, that is x1. Second one is a function of two random variables, that is x1, x2, dot 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 dot. Last one is a function of all the n random variables, x1 up to xn. We will now show that these random variables are mutually independent, statistically independent, and each is uniformly distributed between 0 to 1. Now, obviously, any distribution function, its minimum value is 0, maximum value is 1. So, they are contained within the range 0 to 1, there is no doubt about it. But what is important is that irrespective of, the probability density or then distribution function for this random vector, it could be Gaussian, it could be anything. Irrespective of that, these random variables will always be statistically independent and each one is uniform between 0 to 1. Okay, this is what we will prove. This is a very interesting and useful result. Okay, that is, we will prove that each uniformly dependent between 0 to 1 and yi's I equal to 1 to n are independent. This is what we will prove. Okay. You know, we can just recap a little bit one particular technique, that is, given a set of random variables, okay, and a function of the random variable, say g of x1 to xn, okay, which I can call y. What is the probability density of y? Okay, given a set of functions rather. Suppose you are given x1 to xn and y1 as some g1 x1 to xn, y2 yn is say gn. Okay, so say n functions. So what is the probability density of joint density of y1 to yn? First we said that okay, you want to find out the joint density of this at a particular value of say y1, particular value of y2 and particular value of yn. First step is you put those values in these equations for y1 up to yn and solve. If you get a solution x1, if you get any solution, if you get no solution, say if suppose you cannot find out any x1 to xn for which these equations are simultaneously satisfied, that means this is an impossible case, because you cannot really get that kind of solution for y1 to that kind of result for y1 to yn, okay, in practice, because no x1 to xn will give you that output, that combination of y1 to yn. So then the probability density will be 0. Okay. On the other hand, suppose by putting your specific values of y1 to yn in these equations, simultaneous equations, and find and you get a unique solution, suppose solution is x1 to xn, then the probability density will be p. This is the probability density, joint density of these variables x1 to xn divided by determinant, and not only determinant, magnitude of the determinant, that is with the plus sign, of the Jacobian. Okay. Just a minute. J x1 to xn, where J x1 to xn is this matrix del G1 del x1 dot dot del G1 del xn dot 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 del G n del x1 dot 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 del Gn del xn. Okay. The order of the rows is not important because determinant is invariant to that order. Okay. And if you have got many solutions for a given set of y1 to yn, if you get many solutions, then you simply have to add terms like this. Okay. That is the density function at one set of solution divided by the corresponding Jacobian, the determinant, positive determinant of the Jacobian, again same thing at another solution and like that, and add them. Okay. This is just for the recap. Now, we use this in the example that we considered. In our example, firstly, we quickly write down y1 was only a function of x1, it was not a function of x2 up to xn. So, therefore, that j first is del y1 del x1 and then zeros. Okay, because y1 does not depend on x2 to xn, so corresponding derivatives are 0. Then y2, del y2, it is a function of two random variables x1 and x2. So, del x1, del y2, del x2 and then zeros, dot 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 dot, finally del yn, del x1, it goes to the last term, del yn, del xn. So, it is a lower triangular matrix. Okay. So, determinant is given by just the product of the diagonal elements because upper half is 0. So, that means and the all derivatives, no derivative is negative also, you can easily see. Okay, because every function, every y1, y2, they are distribution functions, and distribution functions are usually having positive slope. Okay. In any case, we will take the determinant and put a positive sign. So, sign is not important here. So, this will be given by just the magnitude of this product. Now, of course, see what is y1, or y1 was f x1. That means, what is del y1, del x1. So, if you differentiate it with respect to x1, you simply get the density now. From distribution, we go to density. So, you get p x1. Then, what is our y2 was f of x2 given x1, right. That means, del y2 del x2. Okay. As I said, all these derivatives are positive for 0, it is because they are not negative, because they are distribution, they correspond to distribution function of some variable, and differentiation is with respect to that variable, like x2 here. And then if you differentiate it with respect to x2, you get the conditional density p x2 by x1, so on and so forth. Okay. Finally, we know y n this leads to the conditional density of x n given x 1 to x n minus 1 and their product. What is this product? This product will be, in this case this product will be what? That is x 1 to x n, this Jacobian determinant, that will be what? P x 1, P x 2 by x 1 dot 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 up to P x n by x n minus 1 up to x 1. Okay? And this is the chain rule that we discussed previously. Okay? So, this is nothing but the joint density of x 1 up to x n. Okay. That means what is P y 1 up to y n is nothing but P, the two p's are not same. This is a probability density of y 1 to y n, it is a defined function, and when I say P x 1 to x n, it is again a defined function. The same symbol P is used. Please do not think that is a function P is same and we once put in y 1 to y n and next time put in x 1 to x n. The two functions are different. In fact, ideally I should put a subscript here x and subscript here y, so that P x, P y they indicate defined functions. But I assume that by now we have attained sufficient maturity. So, we will not be thinking that we have got only one probability density function, sometimes having the variable y 1 to y n, sometimes x 1 to x n. No, that is not the case. The two probability density functions, or rather joint density functions, they are different functions altogether. Anyway, this was the formula. By the way, okay, first let us evaluate what it is. So, if you substitute for this determinant of this Jacobian, okay, you get the joint density function is a positive and the ratio cancels and you get 1. Now, I forgot to mention that Corsair y 1 n as before, that was f x 1, y 2 n that was f x 2 by x 1 dot 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 y what y sorry, there is no n here. Now, each of these functions, mind you, y 1 to y n, they are random variables. Okay, they are random variables. Now, consider any yi can take value between 0 to 1. So, outside that region 0 to 1, its probability is 0, that is yi taking value greater than 1 or less than 0 has probability 0. That is true for all I, that is y 1, y 2 up to y n. So, you can assume an n dimensional hypercube where each axis, one axis corresponds to y 1, another axis corresponds to y 2 dot 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 up to y n, and within each axis you take out a segment 0 to 1. So, you get a hypercube, each side is from 0 to 1, n dimensional. So, each axis, one axis corresponds to y 1, another axis corresponds to y 2 dot 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 y n. So, this y1 to yn, it remains, it takes values within that hypercube with some probability, and probability of they are taking values from outside the hypercube, that is 0. Okay. Further, if you consider any particular value of y1, particular value of y2, particular value of yn within that hypercube, it corresponds to an unique x1, unique x2 up to unique xn, obviously, because consider this equation y1 equal to f x1. For a particular y1, x1 is fixed, that is from the nature of the distribution, okay, because for any x1, f x1 cannot take two values. If f x1 gives the total probability of the random variable x1 taking values from minus infinity up to x1. So, it has got only one value. So, if that value is given, corresponding x1 is known. And then if x1 is known and y2 is f of x2 giving x1, that is that x1, then again x2 is fixed. If y2 is known, there cannot be two x2 giving rise to the same y2, so on and so forth. So, within that hypercube, each point y1 up to yn that corresponds to a unique choice of x1 to xn. So, if you give some specific values of y1 to yn and solve for corresponding x1 to xn, you get only unique solution within the hypercube. Okay. Outside the hypercube, no solution. So, their probability is 0. Okay. Their probability is 0. Inside the hypercube, you get a unique solution. And so, therefore, this is, I mean, you just have to do this once, probability density of x1 to xn divided by the Jacobian determinant, okay, and that is equal to 1. Okay. So, I repeat, their joint density is 0 outside the hypercube, and within the hypercube at any point within the hypercube it is 1. That is interesting, right. So, there is a hypercube in an n-dimensional plane, n-dimensional space. Each axis is given by the random variable, ith axis is given by the random variable yi, I equal to 1 to n. Hypercube, each side is from 0 to 1. In that hypercube, at any point, if you go inside the hypercube, at any point the corresponding joint density of y1 to yn, that is equal to 1. And at any point outside the hypercube, the joint density is 0. Okay. Now, what does that mean? That means, suppose we consider this function integrated with respect to say y in y2 okay. Initially, you can integrate from minus infinity to infinity, but since outside the range 0 to 1 probability density is 0, it is enough that we integrate from 0 to 1, 0 to 1. Okay. And what does this give actually? You can write it, you can write this thing as p of y2 up to yn condition to y1 times p y1. Okay. So, p y1 comes out of the integrals, and the remaining thing when integrated, that will give rise to 1, okay, that will give rise to 1 because total probability is 1. So, this gives rise to p y1, but if I do the same thing on the right hand side, that is I have got 1. So, if you integrate this 1, how many times? If you integrate this 1 from 0 to 1 up to 0 to 1, okay, and with respect to the same variables dy2 dot 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 dyn every integral gives rise to 1. So, 1 times 1 times 1 times dot 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 n minus 1 times 1. So, you see p y 1 equal to 1. So, y 1 is a random variable that is that has value 1 within the range 0 to 1, and outside the range it is 0. Similarly, for y 2, similarly for y 3. Okay. So, each of them, this part we have proved that each random variable here y 1 to y n is a uniformly distributed random variable within the range 0 to 1, okay, and outside that it is 0. And the fact that they are independent is very simple. You can write down easily, since p y 1 up to y n is equal to 1, you can also call it, you can write y 1 like this. After all, each individual density is 1. So, 1 times 1 times 1 times dot 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 1, which is equal to 1, but then that means joint density is nothing but product of individual densities. So, they are statistically independent. Okay. So, that is the proof. Okay, some interesting things we can observe now, because these are very useful in practice. Suppose you got just 3 random variables x 1, x 2, x 3, and you are doing some integration like this. You are given, suppose we first integrate, then we will see. This is given and you are integrating it with respect to x 2 from minus infinity to infinity. What do you get? Well, we can always write it like this. And then this we can write as so only this quantity depends on x 2. So, when this is integrated with respect to x 2 from minus infinity to infinity, that is equal to 1, because it is a conditional density of x 2 subject to some x 1 and x 3, but if x 2 is moved from minus infinity to infinity and this probability density is integrated, you obviously get 1. So, you get this ratio p of x 1 x 3 divided by p x 3, which is, that is, you get p of which is nothing but p of x 1 by x 3. So, that means, suppose in the beginning you are given a conditional density like this, p of x 1 x 2 stroke x 3, that is given x 3, the joint density of conditional joint density of x 1 x 2, suppose it is given, and you want one variable to be eliminated, we want say x 2 to go. What did you have to do? You have to integrate this with respect to that variable. So, we just took the density function p of x 1 x 2 given x 3, but integrated it with respect to x 2 only over the entire range. Immediately you get p of just x 1 by x 3. Okay. I repeat again, if you have got a density function, conditional density function, and this is a conditional line, this slash, to the left of the slash there are some variables, and you want to remove say one of them, or you want to remove say a few of them, then you just integrate this density function with respect to those variables over the entire range, say minus infinity to infinity, those variables which you want to remove. You then get the net thing as a conditional density of the remaining variables. Okay. On the other hand, suppose you have got a thing like this. You have got now suppose 4 random variables, 4 x 1, x 2, x 3, x 4. Okay. And suppose you are doing this integral. X 1 stroke, there is a slash, x2, x3, x4 into P of and integrate with respect to x2 and x3. What do you get? Think for a minute. What do you get? Its purpose I will tell later, but suppose you carry out the integral like this. Well, you can write like this. Okay. There is this conditional density can be written as P of joint density of x2, x3, x4 divided by just the probability density of x4, and they have combined the two. This conditional density of x1 given x2, x3, x4 multiplied by the conditional density of x2, x3, x4. So, that will give rise to the joint density of all the 4 variables x1, x2, x3, x4. Okay. I delete this part. And that joint density you can then write as P of x2, x3, that is the variables with respect to which we are doing the integration, that is x2 and x3. So, x2, x3 slash x1, x4 multiplied by P of x1, x4, that will give us the joint density, and this is divided by P of x4 as before, dx2, dx3. Now, in this integral you see the first function P of x2, x3 subject to x1, x4, only that depends on x2, x3. Now, if that is integrated with respect to x2 and x3 from minus infinity to infinity, you get 1, because this conditional density of x2 and x3. Okay, x1 and x4 are conditioned, but then x2 and x3 are moved over all possibilities from minus infinity to infinity. So, the total value has to be 1. So, 1 times the remaining things, that is P of x1, x4 divided by P of x4. Okay, and P of x1, x4 divided by P of x4 is nothing but P of maybe use different ink. Sorry. Okay, and this is then equal to what? We rewrite what we started with. We started with this. We are given x1 probability density, conditional probability density of x1 given subject to the other 3 variables. If from this, suppose this conditional density is given P of x1 slash the other variables, and if here you want to eliminate some of the variables to the right of the slash, that is the variables which are conditioned, okay, to the right of the slash. If you want to remove some of these variables, in this case x2 and x3, then first you multiply this function by the conditional density of these variables which you want to eliminate subject to the remaining ones, in this case x4, and integrate with respect to these 2 variables. This is what we started with. So, these 2 things are same, these 2 things are same. So, I repeat, if you are given a conditional density function where within bracket you have got a slash sign like this. To the left there are some variables, to the right there are some variables, and from the right you want to eliminate some of the variables, in this case x2 and x3. Then what you do? You multiply this function by the conditional density of those variables to the right of the slash, like in this case x2, x3, which you want to eliminate, condition to the remaining ones, again to the right of this slash, in this case only x4. And after doing that, integrate it with respect to these variables which you want to eliminate, that is x2, x3. Then you get P of x1, x4. Okay. This is a very interesting result, because this comes very handy in practice. In fact, a particular case arises often in practice, and that is called Chapman-Kolmogorov. In this case, often this is written as stroke x2 x3 multiplied by P of x2 by x3 dx2. Okay. Now we have to consider its discrete version. In the discrete version, the random variables x1 to xn, they are not continuous, they take discrete values, some finite set of values that can take, but discrete. Okay. In that case, you can easily extend this logic and write that suppose this conditional probability that x1 takes maybe say xi takes some value ai, x1 say x1 takes a particular value a1, okay, and or ai, alright, x1, for x1 there is a set, we call it alphabet a1, a2, a3 dot 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 dot, out of which x1 is taking a value ai. Condition 2, another random variable say x3, it takes values from another set c1, c2, c3 dot 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 dot, but right now it is conditioned to take the value say ci. This analogously you can write, and you can prove also analogously, as P of x1 equal to ai subject to two random variables, x2 taking say some bk and x3 taking ci. x2 is another random variable which takes values from a set b1, b2, b3 dot dot dot. So, it is bk here, this multiplied by probability of x2 taking bk divided by x3 taking ci, and like we did integration with respect to x2, here it is summation. So, summation over k. So, x2 can take b1, b2, b3, for each case this product is evaluated and added. Okay. A very simple extension of this is the conditional expected values. Suppose there is some condition m and you want to find out expected value of a function of random variables say g x1 to x n subject to m. Obviously, this is nothing but integral of this function multiplied by the conditional density of this subject to m integral this. That is pretty obvious. Okay, this follows from definition, but as a special case we can now consider g to be x1 itself. Okay. So, expected value of say x1 given x2 to say xn, obviously that will be multiplied by this conditional density of x1 subject to integral with respect to x1. Okay. Now, you see one thing, here we have assumed some specific value of x2 to xn, subject to that x1 can take any value and we are taking the mean. This is given by this conditional expected value. Next time again we can change the values for x2 to xn, we can give some other values here and again evaluate this. So, we get another value for this overall mean and likewise. So, that means if you now consider both x1 and also x2 to xn as variables here, not constants, then this entire thing, entire expected value, conditional expected value is also a random variable, but variable, okay. I mean random variable, I mean it is a function of x2 to xn, it is a random variable and it is a function of x2 to xn, isn't it? Here what we have done, we choose a particular value of x2, choose a particular value of x3, there is constants and another constant value for xn, put them here, subject to that, okay, find out the expected value of x1. So, integrate that x1, I mean multiply x1 by the corresponding conditional density and integrate. Next time suppose the values for x2 to xn change, you give some other values. So, obviously, you get another value of this mean, so on and so forth. So, that means this entire thing is a random variable. If you now allow x2 to xn to vary, that is if you now take it as a function of x2 to xn, then it is a random variable. So, what is then expected value with respect to x2 to xn of this mean? That is first you found out the mean and then we are saying that is a function of the other random variables x2 to xn. You give them some specific values, you get one value of the mean. You get another specific values, another set of specific values for x2 to xn, you get another mean and likewise. So, what is the expected value of that? That is if I don't want to take the expectation of what this x2 to xn. So, that means this entire thing now is to be multiplied by the joint density of x2 to xn and integrate it. But if you multiply this integral with respect to p of x2 to xn, you can easily see that it becomes a joint density of x1 to xn, because after all it is a conditional density of x1 subject to x2 to xn. This if you multiply by the joint density of x2 to xn, then the total product becomes just the joint density p of x1 x2 dot 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 xn. That multiplying x1 and integrating will give rise to just the mean of x1. That is earlier we had dx1, now dx2 to dxn. So, this product of the two probability densities, one is conditional and this joint, that is the joint density of product becomes equal to the joint density of x1 to xn. That multiplying x1 and if you integrate it with respect to all the random variables, obviously that will give you the mean of x1. It is because joint density can be written as p of x2 to xn subject to x1 multiplied by p of x1, and the first one when integrated with respect to the respective variables will become 1. So, we will be left with x1 multiplied by p of x1 integrated from minus infinity to infinity with respect to x1, that will give rise to the expected value of x1. Since we have done similar things in the past, I am not getting into those lines. Okay. Similarly, Just as an example, suppose we are considering a case of 4 random variables, okay, and you found out E of x1 subject to x2, x3, x4. Now, suppose here when you just write this, it means that you have given some specific constant value for x2, specific constant value for x3, same for x4, and finding out this mean. Now, suppose here I am not changing the values for x2 and x3, but I am changing only x4 from case to case, and obviously the overall mean changes. So, this mean is then a function of x4. Okay. So, what is the expected value of this mean with respect to x4? So, that means I have to take this, I have to take this and multiply by, here is it is interesting, multiply by what? Will it be just the probability density of x4? Answer is no, because in this entire business I am keeping x2 and x3 fixed. Subject to that I am varying x4, right. So, that means I have to multiply by this and then integrate with respect to x4. And what will this give rise to? You consider this expression, it was E of x1 given x2, x3, x4, and there I took the further average over x4. So, I am left with nothing but just E of x1 given x2, x3. So, that means given a conditional expected value, this say this, consider this and this one and this one, given a conditional expected value of x1 subject to a set of random variables, that is there is a slash, to the right of the slash there is a set of random variables. If you want to eliminate say a particular random variable or a few random variables, like in this case x4, what you have to do, you take this conditional expected value, but multiply it with respect to the conditional probability density of those variables which you want to eliminate, in this case x4, subject to the remaining ones to the right of this slash, that is x2, x3, and integrate with respect to those variables like x4. Okay. And it can be easily extended to the discrete case, that is E of say x1 subject to say x3 taking a value say CR, because x3 takes values from a set C1, C2 dot 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 dot. So, this is specific now. With respect to this, that is, this is called the condition, what is the mean of x1? You can easily extend this logic, you can make a summation over k E of x1 given x2 equal to bk, x3 is equal to CR multiplied by the probability of x2 is equal to bk divided by x3 is equal to CR, and summation over k. Like earlier we had integral, now we have summation. So, that is all for today. So, in the next class we will be considering the characteristic functions for this general case of random vectors. Okay, we will derive some interesting properties, we will march towards what is called central limit theorem from that. Okay, so all that for next class. Thank you very much. So far we have been for last few lectures only we have been on this topic. So, today we will be considering characteristic functions for random vectors. See, you remember, I mean earlier we considered only a single random variable, and with respect to a single random variable we consider a characteristic function. So, that time it was a function of just one frequency variable omega 1. Then we extended that to the domain of two random variables. So, that time also we had a characteristic function, it was a function of two variables, two frequency variables omega 1 and omega 2. So, now that whole approach will be generalized to a random vector that has got say n number of random variables, right. So, we will be considering random x1, x2 dot dot say xn. Okay. There are n random variables, they are jointly random, they have got a joint density, that is you can say the joint density, joint probability density, this is for probability. Obviously, you can understand that since there are n random variables, we will have n frequency variables now, omega 1 associated with x1, omega 2 associated with x2 dot 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 omega n associated with xn. Okay. So, the characteristic function, I mean if I define a vector, in my case all vectors are actually column vectors, whereas in the book by Papoulis he normally takes vectors as row vectors. There is a difference you may find. Okay. This is row, if you put a transpose it becomes a column vector. Okay. So, the characteristic function actually dot sigma n, okay, 2 pi to the power n square root into exponential minus 1 by 2 sigma 1 square minus 1 by 2 sigma 2 square dot 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 minus 1 by 2 sigma n square. It amounts to just multiplying n individual Gaussian density functions for n random Gaussian random variables that have 0 mean and variances sigma 1 square, sigma 2 square dot 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 sigma n square. So, we stop here today. In the next class we talk about stochastic convergence and we go towards central limit theorem. Okay. Thank you very much.